Hi everyone, this is a joint work with other people in Roma 3 and University of Pisa. And so let me first introduce very briefly what is community detection, as probably everyone knows about. So in community detection, one wants to organize nodes of a graph into clusters, okay? So clusters, you have many edges joining nodes of the same clusters. And of course, you want to have comparatively few edges joining nodes of different clusters, okay? So it's something like that. So that is very great important in sociology, biology, and computer science, of course. Okay, so our first intuition is that enumerating cliques is a very common definition of community. So communities can have different definitions, and cliques is probably one of the most common definition. In a clique, every node is connected to every other node except itself. So in the graph, so that's very trivial, okay? So in theory, the problem is very hard. So in theory, the problem is NP hard. But in practice, we do have many efficient methods for computing and enumerating cliques in real-world networks. Unfortunately, cliques may not be the very most practiced way of enumerating communities, because in real-world networks, you may have missing links due to noise, and somewhat the definition of a clique for community is somewhat too restrictive. So the idea is to have a relaxed definition of community, which is the k-plex, okay? So in k-plex is something where you have every node connected to other nodes except at most k. So in a clique, you have every node connected to other nodes except itself, and in a k-plex, you have every node connected to every other node except k. So that means that you have a clique that it is a one-plex. Okay. So state-of-art methods, there are state-of-art methods for computing and enumerating k-cliques, all of them, but they can process only, very small graphs, only hundreds of nodes. So in practice, you spent a lot of time for enumerating k-plexes, and you must find k-plexes that are not significant or very small. Okay? What means not significant or very small? So for instance, since you have this k-parameter to play with, you may have some k-plexes of size k that turn out to be very sparse. So for instance, if you have a 10-plex of size 11, most of the nodes may be not connected at all. Okay? So as a community definition, it's not very meaningful. In another case, you can have k-plexes of size smaller than 2k, can have very high diameter. You can prove that. So for instance, if you have a 6-plex of size 11, so means that the size is larger than 2k, you may have also structures that have a very high diameter. Okay? That is something that you can prove analytically. So in general, what does this mean in practice is that k is supposed to be small with respect to the size of the structure itself. So that looks like a quasi-clique. So you can have 2-plex of size 6. So that makes more sense as a definition of community. Okay, so that means k-plex is somewhat hard to use because you have this k-parameter that you need to tune. Okay. Also, most k-plexes may be very small. For instance, this is the distribution of 2-plexes and 1-plexes in one sample network. And as you may see from the plot, you have that the 60% of cliques have size smaller than 6, so almost trivial. And you have that very few 2-plexes have size larger than 10. And at the end, you can say that most k-plexes lie in a long tail. So where are we? We have that the k-parameters can make some k-plexes not significant, and also some k-plexes can be small. So what is our approach to make all those things easier to use is to focus on large k-plexes. Okay? So we don't want to enumerate all of them. We don't want to enumerate all k-plexes. We don't want to fine-tune k and the size and whatever. We just want to focus on what can be defined as large k-plexes. So one way of defining large, which we believe is something meaningful, is to define large with respect to the size of the largest clique. Okay? So let omega be the size of the largest clique. For instance, one k-plex could be considered large if it is larger or equal than omega. Okay, so that's something very intuitive. We are not restricted. We can use any threshold for k-plex size, but one reasonable threshold could be the following, the size of the largest clique. So the intuition is that nodes in large k-plexes, where large is defined with respect to the size of the largest clique, have certain properties. Okay? So we will enumerate only subgraphs that have those properties. So the properties that we are looking for and that we prove analytically in the paper are easy to test and are necessary but not sufficient. So we will restrict our search to subgraph having those properties and using those properties as filtering and search heuristics. So at the very end, what we did in the paper is to formulate a heuristic for enumeration. At the very end, when we describe those subgraphs having those properties, we can use state-of-the-art tools for just enumerating k-plexes, okay? In practice, what we achieve is that while state-of-art methods can process only hundreds of nodes, we can process in much smaller time hundreds of thousands of nodes. So before it was hours and days, now it is seconds, which is kind of heuristic. So it's something that we still NPR problem, right? Okay, so that is one example. We have a very simple graph here. Okay, in this graph we have 16 nodes. The largest clique has size 5, and consider that we want to find 2 plexes. So as I said previously, 2 plexes can be, you can have a lot of them also in very trivial structures. For instance, in this simple graph you can have 37. Okay, of course, most of them are very tiny. I hadn't the time to draw all of them, of course. I've been searching on only the first few of them, but trust me, you have 37 of them of size 3, 4, right? But only 2 k-plexes in this particular graph are larger than omega, larger or equal than omega. You have the largest clique itself, which is a 2-plex, of course, because it is also a 1-plex. And you have the yellow graph. This is a 2-plex of size 6. So if we were willing to enumerate all the 2-plexes in this graph, we need a lot of running time. But if we are able to focus ourselves only on the colored structures, then we can do something much more efficient. That really boils down to get rid of the crossed nodes. Okay. So for getting rid of the nodes that we don't want to process during our enumeration, we need to identify what properties they don't have. So first property is coherence. So we were able to prove that nodes of a k-plex having size larger or equal than m have coherence larger or equal than m minus k. So we can safely ignore all the nodes that have coherence smaller than that. And of course, it turns out that in this particular graph, all the nodes above marked with the red cross has coherence smaller than 3. Here we have m is the number of nodes, omega is the number is the size of the largest clique. So if you just get that you can filter out everything having coherence smaller than 3. Okay. So the first 3 nodes are gone. Second criterion is cliqueness. So we could prove that nodes of a k-plex, okay, I'm not drawing all the red of the nodes above because we already filtered it out with coherence. So now we need to filter out the nodes below. We can do that with cliqueness. We were able to prove that nodes of a k-plex larger or equal than m have cliqueness larger or equal than m over k, not minus, okay? Cliqueness, actually it's a term that we introduced. We said that the cliqueness of a node is D if D is the size of the larger clique it participates into. Okay, so this time we need to filter out everything having cliqueness smaller than 2.5, and also the nodes below go out. Okay? So that is okay for the toy example. in practice, we were able to prove that most networks that have social network properties, using those criteria, you can get rid of more than, I don't know, 95% of nodes. So it really remains nothing to process. Okay, and you can really use actually also trivial enumeration techniques, and that will not last longer than seconds of computation. So specifically here, I have a plot. In the plot, you have the y-axis is in log scale, and you have the number of nodes surviving the coreness and cliqueness criteria applied. So the black line is the number of nodes, okay? And the red, blue, and green bars represent the number of nodes after applying the two criteria. And as you can see, that's log scale. Most of them really are left with with few hundreds of nodes that can be processed using state-of-the-art methods. That's on the other plot is really the same information, but plotted with fractions instead of absolute numbers, okay? Note also that one particular graph, and we will see later why, cannot benefit from our heuristic, as filtering does nothing here, and all the nodes really are left, okay? We will see why. Okay, so in general, we have up to 4 order of magnitude reduction, okay, and in one particular instance, we have no reduction at all. So that was for filtering. But also, after filtering, we need to find out something for enumerating things efficiently. So we call this our last criterion the overlapping cliques criterion. So the overlapping cliques criterion says that k-plexes larger or equal than m are included in sets of overlapping cliques, each of size greater or equal than m over k. I'll show you that with a figure. Okay. So in the figure, we have that the 2-plex of size 6 of our toy example. It's made of, as you can see in the circles, it's made of 3 cliques with overlap for 1 node. So that's a way for finding out enumerating k-plexes in the surviving nodes, okay? So the application is that we select a clique as a kernel. So we enumerate all the cliques, and we said that it is easier in practice. Every clique is selected as a kernel. We look for overlapping cliques, as in a flower, you may say. And those flowers of cliques correspond as the subgraphs that we use for enumerating k-plex into. Okay, we'll see the algorithm. So for instance, if we look at the kernel clique, we will process only the circled nodes around. That, of course, can be done in parallel, because those graphs can be processed in parallel, and every clique and every kernel can be processed separately and very efficiently. So the final algorithm looks as in the slide. Sorry, because that was supposed to be black. I don't know what is gray, actually. And so first step, it's easy. We filter out nodes that don't match criteria of cliqueness and coreness. In the second step, we compute cliques, and that's easy too in practice. In the third step, for each clique, and that can be done in parallel, we select the overlapping cliques, and then we enumerate all the k-plexes in the overlapping cliques with state-of-art techniques. And that's the hard part. That's the bottleneck of our algorithm. That's the bottleneck, right? But typically, at this point, we have very few nodes left. So I'm showing some running example. Okay, so let's start from this graph. This graph contains hundreds of 2-plexes, and so that is the first clique that is selected by our algorithm. If we look in the neighborhood, that's the set of nodes resulting from the overlapping clique criteria. We can find the k-plex. If we go to another clique of the original graph, we just look in the neighborhood of overlapping cliques, and we find the other plex. Okay. And finally, if we go to the last clique, which is selected by I'm selecting only 3 cliques because those are the only 3 cliques surviving the size filter. If you look in the neighborhood of overlapping cliques, again, we find out the final k-plex. And the k-plexes that we found are the only k-plex that are larger or equal than the larger clique. Okay, so we have 3 plexes found out of more than 400 k-plexes originally. So let me conclude with a couple of experiments. Okay. So in this table, I'm showing running times for our algorithm compared to a full enumeration technique. Okay. So we are not showing a new algorithm. If you will, this is a meta-algorithm in a sense, because it's just filtering and focusing things, but at the very end, we use the classic enumeration algorithm in the subgraph that is left. So by enumerating things with the classical algorithm, we get more than 6 hours everywhere except for the first graph. The first graph contains just less than 200 of nodes. With the new algorithm, after pruning things and nodes with corners, cliqueness, and only focusing on sets of overlapping cliques, we do seconds. Hours, seconds. And the only exception to that is the Newman graph that, as I told you, doesn't change much after the application of our filtering. And that's actually the weakness of what we did, okay? Because and that's why the reason is that, as you can see in the column where we have the max clique number, look at the Newman clique, the max clique is 3. So it's a very small number, and that will give you very small thresholds, resulting in no filtering at all in practice. So you really have the same graph that you had before, so no surprise that the enumeration have still more than 6 hours running time. Finally, I'm showing some experiments for finding all the k-plexes not larger. I told you that one reasonable way is to look at k-plexes larger or equal to the largest clique, but it's not a limitation. You can do any m. So here m is set to 80% of the size of the largest clique. And you get slightly similar results, even though the running time this time is somewhat higher. Okay? So finally, the conclusions. We said that cliques maybe are a common definition of communities, but in practice, this is too restrictive. So k-plexes are still formal way. Okay? Still a formal way for defining communities, but maybe more flexible and meaningful in practice. We proposed heuristics for enumerating large k-plexes efficiently. Okay? And our intuition is that a relevant portion of the network can be filtered out before even starting enumeration, and that cliques that can be computed efficiently in practice, not in theory but in practice, can be used as a starting point, as a guide for all the subsequent heuristic steps. And graphs with hundreds of thousands of nodes can be processed in really few seconds. So other open problems are use other primitives. We are still using the plain old k-plex enumeration technique as a final step. So maybe you could improve by using a more efficient primitive and understanding, that it is only a heuristic, what it makes bad about distance. So one intuition is that if the largest clique is small, you can filter that much. But that's not really the complete story. Maybe there is something deeper that makes a graph running slow under our heuristics. Okay, so my time expired, so thanks for your attention.